Okay, so let's continue. Next topic. Next topic is number 005. Okay, let me see. It's a little bit difficult, but I try to explain as clearly as possible. So this is like page 7. There is an example about skew symmetry. If Aij is a skew symmetric matrix, solve the system of equation. Yeah, the question is what is a skew symmetric? What was the skew symmetric? Was there an explanation about skew symmetric? Let me see. Skew symmetric. See, this is also called anti-symmetric. Anti-symmetric. Yeah, this is also called anti-symmetric. So skew symmetric is something like this. Let me write down. Skew symmetric. If Aij is skew symmetric, this should satisfy minus Aji. Skew symmetric. This is anti-symmetric. Anti-symmetric. Okay. So if A is skew symmetric, solve the system of equation like this. So let's solve this. Now we use epsilon delta identity to get. So here we just simply multiply this one, this one. Then here the summation is assumed. Summation on I is assumed. Then you can see, you can E I M K I M N E I J K. This is actually equal to E M N I E J K I J K I. So then this I is dummy variable, so you can put K like previous previous case. I'm sorry, I have already used the K, but in the previous formula, we use the K for the repeated index. Yeah, but in this case, actually the I is the M and I is the repeated index. So JKI is the repeated index. So we this one. So this part was replaced to this. Yeah, we use just MN and JK. MJ NK minus MK NJ. Yeah, and this part is the same. So then we will see JK is repeated. It's very complicated. Both J and K are repeated. Understand? So here you can see this first term. This multiplies this delta Mj delta Nk and Aj K. So let's first repeat J. J, we repeat J. So J will hit M eventually. Because M can be 1 or 2 or 3. And J goes from 1 to 3. So J will hit M at some point. So this will eliminate it. And J is changed to M. Then we let K change. K change. K will eventually hit M, N, N, right? So this will, then K is changed to M. So this go to A, M, N. And let's see the second term. Second term is, let's see, we have delta NK, MK, delta NJ, then A, JK, right? So K is repeated. So we run K from 1 to 3. So it will hit M. So this will be, this hit M. Then J is repeated. So J will hit N. So this will this disappear. Then J go to N. So eventually we will have AMN, AMN minus ANM. That's this. AMN minus ANM. Then this way. Right? So then you have anti-symmetric property. So MN minus NM, but this one is equal to AMN. So this is like 2. This thing is 2 AMN. So then this. So you just divide both sides by 2. So you eventually get this one. Yes. Where we used the skew symmetry property AMN equal minus IA minus AMN. Yeah. Okay, so now we go to 2.2.2 example products. If Aij is symmetric, Aij is symmetric, what does it mean? Aij is symmetric means Aij equal Aji. This is symmetric. And Bij is skew symmetric. Again, skew symmetric means Bij equal minus Bji. This is a skew symmetric. Okay. So this is skew symmetric. Show that Aij, Bij equals 0. So let S equal Aij, Bij. If we interchange dummy indices, I go to J, J go to I, we have S equal Aij, Bji. Yeah. Using the symmetry of A and the skew symmetry of B, we can write this as S equal Aij minus Bji minus Bij. This one, I think. This one goes through like this. So A, you can change I and J. For B, if you change you need a minus sign. So then this equal minus aij, bij from here. So then this go to minus s. Minus s comes from here. This is this. This guy is s, as you can see here. So minus s. Then you get minus 2s equals 0, s equals 0. Yeah, that's a proof. So if you have symmetric matrix and anti-symmetric matrix or skew matrix, then this is not matrix multiplication. This is not matrix multiplication. You have I, J, J. So this is more like you have A1, 1, B1, 1, plus A1, 2, B1, 2, plus A1, 3, B1, 3, plus A2, 1, B2, 1, plus A2, 2, B2, 2, plus A2, 3, B2, 3, plus A31, B31, plus A32, plus B, sorry, B32, B32, plus A33, B33. So this is very strange sum. This is very strange sum. If you have A11, A12, something like this, and B11, B12. So this multiplication is just you multiply this on this. So A11, B11 plus then you have this and this A12, B12 plus blah blah blah. So this is not regular matrix multiplication, but a strange product. This is not usual matrix product, but strange product. And you have coordinate system. As shown in figure 2.2, we use a proper right-handed Cartesian coordinate system with x1, x2, x3 denoting the three axes. A directed line segment from the origin to any point in this 3D space is called position vector R with components xy, x2, x3 along the three axes. We also use the notation x instead of R at times. In matrix notation, using a column vector, we have R equal x equal x1, 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 x2, x3, defining unit vector or base vectors E1, E2, and E3 as E1 is 100, E2 is 1010, E3 is 001. We can write R equal x1, E1, x2, E2, x3, E3. The dot and cross product of the unit vector can be expressed with the Kronecker delta and permutation symbol in the form like this. How do we prove it? How do we prove it? Yeah. I don't know. So this is like E, like 0, 1, 0, and the other one can be 0, 1, 0. So if this is I, J, K, or how do you call this? 1, 1, 2, 3, 1, 2, 3. So if you have 1 at the same position, then you will have 1. If the position of 1 is different between these two vectors, then you get 0. This product is 0. So this property is just Kronecker delta property. So I and J has to be same number in order for this product to have a value of 1. If I and J are different number, this product EI dot EJ becomes 0. Yeah. And this is cross product is more complicated. And I don't know, I usually don't use this notation, but let's see. So these three number has to be different, right? So because we learned EIJK property, so this IJK three number has to be different in order for this to have 1 or minus 1. If any two of them become same, then the value of EIJK is 0. Yeah. So here, in order for this EIJK to have value, I and J and K has to be different. I, J, K has to be different. So this can be like this. 1, 0, 0 times 0, 1, 0. Then there is some factor. Then you have 0, 0, 1. Yeah. So, or this has to be different. 1, 0, 0 times 0, 0, 1. This is also okay. Then you have some factor. Then the vector has to be 0, 1, 0. Yeah. So there's another vector you can think like here 0, 1, 0 multiplied by 1, 0, 0. So then you also have some factor times 0, 0, 1. And you have another one. 0, 1, 0 multiply cross product and 0, 0, 1, for example. And you have some factor, then 1, 0, 0. Yeah. And you can also come up with another 0, 0, 1 times 0, 1, 0, 0. Yeah. And this goes to something multiplied by 0, 1, 0. Then the last 0, 0, 1 multiplied by 0, 1, 0 go like something multiplied by 1, 0, 0. Yeah. And this something, the something, what I call the something is something, 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 something. This is EIJK. this one. Yeah. So here I is 1, j is 2. So here you have to have epsilon e 1, 2, 3, which is 1. For this, I have 1, 3, 2. So this here you have e 1, 1, 3, 2, which is minus 1. Yeah. So here this one, for example, 2, 1, 2, 3, 1, 2, 3, 1. So E 2, 3, 1 is 1, right? 2, 3, 1. You permutate twice. So this is 1. Here is 1. So this part you have epsilon 2, 1. This is 2, 1, 3. Yeah, 2, 1, 3. You permutate once. This is minus 1. This is 3, 1, 2. 3, 1, 2. Epsilon 3, 1, 2 is 1. You just permutate once. You can permutate twice. You permutate is you change. Permutate. You change 1 and 3. Then you change 3 and 2. So this is 1. And here 3, 2, 1. So E 3, 2, 1. This one you permutate once, twice. How do you permutate once, twice, 3 times. So you have to permutate 3 times. So this is minus 1. Do I have everything? So I have this one, 3, 4, 5, 6. All possible combination. Yeah. 3. I think I gave all possible combination. Yeah, I think so. So this is the meaning. This is the meaning of this cross product. Okay. So we can go on next part. Coordinate transformations. 2 types of coordinate transformations are encountered frequently in our studies. Coordinate translation and coordinate rotation. If we denote the new coordinates of a point P by xi prime, in the case of translation, the two systems are related in the form x prime I equal xi plus hi, where hi are constants. This shows in figure 2.3 coordinate translation. Yeah, so you had interesting. To me, this is coordinate translation. So P is the same point. So you just had one coordinate, unprimed coordinate, which is x1 and x2. Then you have another coordinate. Another coordinate is called x prime, x prime 2. Yeah. So this difference is h. HI and H2. Okay, so next one. Rotation. Coordinate rotation. Let us consider first a rotation of coordinates in two dimensions. The origin remains fixed, and we obtain the x1 prime axis by rotating x1 axis counterclockwise by an angle theta. As shown in figure 2.4, the two systems are related in the form x1 x prime 1 is x1 cosine theta x2 sine theta. It's a little bit complicated, right? This go to theta. x1 cosine theta. See, I think to me it's more easy if I consider this way. You have xy. So originally you have this one. So you have this one, right? So this is x1. This is x2. Then this theta rotation, yeah, actually means this way. This theta rotation. Then you will have x2. This is x1 prime, and this is x2 prime. This is x2. So I don't know. Isn't this better? I'm not so sure. So then this theta rotation, I would say this rotation, this theta rotation, this theta rotation, yeah, you can see this one change. Let's see. Let me use blue. This one will change. You had x2, you will change this part. Yeah, this will change this way. So new one. x1 actually goes to sine theta. And this x2. No, I'm sorry. So this is x2. So I have x2. Then this one is x2 prime. I should use red. So x2 prime equal, this is equal actually cosine, this is theta. Cosine theta x2, right? Then here x1, sorry, I have to use red. x1 prime is sine theta x2, yeah, x2 goes sine theta. Does it make sense? So same way, you can consider x1 here. Let me see. Let me just use blue color. Yeah, blue color. So this is wrong. So let me use just blue color. So this rotates theta this way. So x2 prime goes like minus sine theta x1. x1 prime equal cosine theta x1. Yeah? So I think this makes sense. So we have x1 prime, x2 prime, yeah, and x1 prime is cosine theta. Sorry. This is cosine theta. Is it strange? Cosine theta. No, it's okay. Cosine theta, sine theta. Yeah, then minus sine theta, cosine theta. x1, x2. Does it make sense? So you have x2 here, which goes to x2 prime by cosine theta. So this cosine theta goes here, and x2 and x1 prime is connected by sine theta, so which is this, and x1 goes to minus sine theta to x2 prime, x1 cosine theta, which goes to x1. Yeah, this is correct. So let me check. This way you can see x1 prime is cosine theta x1. Oh, it's okay, right? Cosine theta x1, sine theta x2. Yeah, correct. And x2, if you go x2 prime, you see a minus sine theta x1, cosine theta x2. Yeah, so this makes sense. So then you can make an inverse. We obtain the inverse of this transformation by replacing theta by minus theta. Yeah, minus theta. So you can now you change prime, unprime, prime to unprime, unprime to prime, unprime to prime, unprime to prime, unprime to prime. Then you see it also change theta to minus theta. So sine theta go to minus sine theta. Cosine theta doesn't change. Cosine theta doesn't change. Minus sine theta go to sine theta. Something like this. Yeah. So equation 236 can also be written in matrix form. Q1, this is what I wrote. This is what I wrote here. This is matrix form. So Q11 equal Q22 equal cosine theta. Q12 equal minus Q21 equal sine theta. Using column vector x prime and x and square matrix Q, we have x prime equal Qx. A node of caution is in order at this point. We have absolute vectors in space, such as R, and then we have column representation of the components in a chosen coordinate system, such as x and x prime, when there are no coordinate rotations involved. We do not have to distinguish these two representations. When there are coordinate rotation, we use R for the absolute vector. Does it make sense? A node of caution is in order at this point. We have absolute vectors in space, such as R. Then we have column representation of the components in a chosen coordinate system, such as x and x prime. When there are no coordinate rotations involved, we do not have to distinguish these two representations. When there are coordinate rotations, we use R for the absolute vector. Okay. So this is something like this. I don't know. Okay, absolute R. This is just this point, So this point, if you use primed coordinate, this can be expressed like x1 prime, x2 prime. If you use unprimed coordinate, this is x1, x2. Yeah? So this expression, see this number, x1 prime and x2 prime, are different from x1 and x2. These are different numbers because we use a different coordinate. But these 2 points are actually the same point, which should be called R. Yeah. So this is called absolute vector. This is called absolute vector. Is it absolute? Say, yeah. So this is called absolute vector. Yeah. Another way to relate x prime to x is by use of two systems of unit vectors EI prime and EI. Let us do this for the 3D case. The position vector R has two representations. R equal x1 prime E1 prime plus x2 prime E2 prime plus x3 prime E3 prime equal x1 E1 plus x2 E2 plus x3 E3 because E1 prime, E2 prime, and E3 prime are mutually orthogonal. Taking the dot product of the preceding relation with E1 prime gives. Yeah. So I don't know if you know this. Now we want to obtain this one, x. So x1 prime can be obtained. You just are dotted with E1 prime. This is how you get x1. And for R represent, if you use this one for the R representation, you just plug this into here. So then you obtain this one. See, I can say this, that maybe we can write E1 prime dotted with R. Right? Then we put R expression here. So E1 prime dotted with E1 times x1 plus E1 prime dotted with E2 times x2 plus E1 prime dotted with E3 times x3. The elements of the 3 by 3 Q matrix associated with the rotation are the dot product of the unit vectors. See, this is the interesting part. This is a lot of mathematics. A lot of mathematics. See, I can say this way. See, here we want to know this matrix. Right? We want to matrix which can convert x1, x2, x3. Then you have q, 1, 2, q. Sorry, I have 1, 1, q1, 2, q1, 3, q2, 1, q2, 2, q2, 3, and q3, 1, q3, 2, q3, 3. Yeah. Then we have this. We have here x1, x2, x3, right? So now look at this equation. This equation, so you can identify this way. Q11 here is this. Q12 is this. Q13 is this. Yeah? So this identification is this one. Q12 is E1 prime E2, Q13 is E1 prime E3. Yeah? Then next, let us do this using the index notation and summation convention. Okay, anyway, I think I want to stop it here. Here, I stop. Yeah, I stop. So this is what? Page 11. I stop at page 11. Yeah? 242. So I can write this up to page 11. Equation 242. Okay. So I can continue next time. It's already 46 seconds, 46 minutes.